Hello girls, today we are going to see a theorem. If V is finite dimensional and W is a subspace of V, then we are going to prove W star is isomorphic to V star by E of W. For proving this theorem, we are going to make use of the first fundamental theorem. The statement is, if T is a homomorphism of U onto V with kernel W, then V is isomorphic to U by W. That is, V is isomorphic to U by W, where W is kernel of T. For that, what we are going to do is, we are going to define a map capital T here as V star to W star as T of F is equal to F restricted to W. And we are going to prove this T is a homomorphism. Since in the first fundamental theorem, we have to take T as a homomorphism. So first we have to make sure this is a homomorphism. For proving that, what we are going to take is, we are going to take two elements F and G belongs to V star and alpha and beta belongs to F. We are going to prove T of alpha F plus beta G is equal to alpha into T of F plus beta into T of G. Then we can say T is a homomorphism. So we are going to start with T of alpha F plus beta G, which is equal to, from the definition of T, it is alpha F plus beta G restricted to W, which is equal to alpha into F of W, F restricted to W plus beta into G restricted to W, which can be rewritten as alpha into F of W plus beta into G of W, which is equal to alpha into T of F plus beta into T of G. Therefore, we can say T is a homomorphism, and we have to confirm T is onto. Clearly we know that T is onto. From the definition of T is a map from V star to W star. No, we have defined that as T of F is equal to F restricted to W. Therefore, we can conclude for every element in W star, we are able to find a pre-image in V star. So, we can say this function is onto. Next, we are going to prove kernel of T as A of W. Already we know the definition of kernel. No, kernel of T is nothing but, we have to take any two vector spaces U on V, and T is a map from U to V, be a linear transformation. Then kernel of T is nothing but the set of all elements U belongs to the first set capital U, such that T of U equal to 0. Here we are going to prove kernel of T here as A of W. Kernel of T here as, we have to take one element from the first set, that is V star, such that T of that element is equal to 0, T of F equal to 0. From the definition of T of F is equal to F restricted to W, no. So F restricted W equal to 0, that is F of small w equal to 0. This is the definition of A of W. Already we have seen no A of W. It is equal to F belongs to V star, such that F of W equal to 0 for all W belongs to W, capital W. Therefore, kernel of T is equal to A of W. Therefore, we can use, now we are going to use the first fundamental theorem, and we can conclude W star is isomorphic to V star by E of W. The next one is the corollary. If W is a subspace of a finite dimensional vector space V over F, then we are going to prove dimension of the annihilator is equal to dimension of the vector space V minus dimension of W. From the above theorem, we know that W star is isomorphic to V star by E of W. Taking dimension on both sides, dimension of V star is equal to, the right side can be written as dimension of V star minus dimension of E of W. Already we have seen one theorem based on this, no? Therefore, dimension of A of W is equal to dimension of V star minus dimension of W star, which is equal to dimension of V minus dimension of W. Since we know that dimension of V star is dimension of V and dimension of W star is equal to dimension of W. Therefore, we got the result, dimension of the annihilator is equal to the dimension of vector space minus dimension of the subspace. The next one is corollaries. Corollary 2. If W is finite dimension, if V is finite dimensional and W is a subspace of V, then annihilator of A of W is equal to W. That is, A of W is equal to W. This is an important corollary. For proving this corollary, what we are going to take is, W is a subspace. Since already it is given, no, W is a subspace of V. W is a subspace means it is a subset of V. Therefore, A of W is a subset of V star. Taking annihilator on both sides, that is A of W is a subset of, here the first one is V star. So for that again we have to take one star, that is V star the whole star, dual of the dual set. We know that if we are going to take one map psi from V to V star the whole star as psi of V is equal to the function t suffix v for all v belongs to v, t suffix v belongs to v star the whole star, which is equal to home of v star comma f. That is, t of v is the function from v star to capital F, and we are going to define that in such a way that tv of f is equal to f of v for all f belongs to home of v comma f. In particular, we can take tw of f is equal to f of w for all f belongs to v star and w belongs to capital W. Let one element f belongs to a of w. From the definition of a of w, we know that f of w equal to 0 for all w belongs to capital W. Therefore, we can say tw of f is equal to f of w, which is equal to 0. Therefore, tw of f is equal to 0. Therefore, we can say this tw belongs to the annihilator of a of w. Therefore, a of w is a subset of a of w, which implies w is a subset of a of w for all functions f belongs to a of w and for all small w belongs to capital V. Therefore, we can say w is a subspace of a of w. From corollary 1, we know that dimension of the annihilator is equal to dimension of v minus dimension of w. Therefore, we can use the same theorem here, same corollary here as dimension of of w is equal to dimension of v star minus dimension of annihilator of w, which is equal to dimension of v star is dimension of v. Therefore, we can replace the first one as dimension of v. The second one, dimension of of w, can be replaced using the first corollary as dimension of w is equal to dimension of v minus dimension of w. And dimension of v and dimension of v get cancelled. So finally we are having dimension of w. So dimension of of w is equal to dimension of w. Already we have w is a subset of of w and both the dimensions are equal. Therefore, we can say both the sets are equal. W is equal to of w. Is it clear, girls?